Hi guys, in this video we're going to talk about geometric proofs, proving triangles congruent, using the definitions involving bisectors and midpoints. First we're going to talk about the definitions, then we're going to do 4 examples. Alright, let's get started. Alright, so let's keep this simple. If C is the middle of a line, or we have a point in the middle of the line, we call that a midpoint. Well, if it's in the middle, all that means is that each half of that line is congruent, or the same. So, if I know C is the midpoint of AB, I can make a statement here that line AC is congruent to line CB, or something like that. I'll discuss the reasoning language later, but essentially if we know we have a midpoint, we have 2 equal parts of a line. Same goes for the angle bisector. A bisector for a segment or an angle essentially do the same thing as a midpoint. But to cut an angle in half, we do need a line. We can't use the point. The point at the middle of the angle is already called the vertex. So this line here is called the vertex. This line here cuts that angle in half. And it's creating these angles. Angle A, B, D, which would be congruent to angle CBD. I discussed in my previous video how to write and read these angles. Like I mentioned in that video, that's a struggle for students, and it's one of those things that take time to learn. Now, the segment bisector does essentially the same thing as the midpoint, but it's a bisector. You can't, though these things do the same thing to an object, you cannot interchange this language. In other words, a midpoint is a point and a bisector is a line. And in your reasoning, you need to make that clear. But here, because I have a bisector, it looks just as it did before. I would say AC is congruent to CB. Be careful here. So, if this was a sandwich, which I do like sandwiches, DE is the knife cutting the sandwich AB in half. DE, being the knife, is not being cut in half by the sandwich AB. It is not reversible, which is a common mistake students make. Okay, let's take a look at the next example. Okay, this is a very unique proof. It's a proof designed just to showcase the difference between a bisector and a midpoint. So, just as I've done in my other proof videos, I am going to copy down the given before I try to handle the problem. Okay, I don't want to address the first 2 givens yet. So, I want to get off my plate angle CAD is congruent to angle CBD. The diagram was nice enough to label these angles for us. Remember, the letter in the middle is indicating the vertex, and the surrounding letters of the angle are stating which direction the angle is opening in towards those points. So that's what's going on there. I cannot use the reflexive side here. I'll discuss that in a second once I address the angle bisector. So the angle bisector is saying that this large angle at the top here, ACB, is being cut in half by line CD. The way I can address that is it's going to give me two congruent angles, because bisecting means cutting exactly in half. So now I know here this angle ACD is congruent to this angle BCD, and I could use that to forward my proof. So I mentioned earlier, there's a number of ways to defend an angle bisector or a midpoint. Typically what you see in formal proofs is angle bisector followed by definition. My recommendation, as I mentioned in the previous video, for us beginning provers, is to just use the language in the given. You know that angle ACD is congruent to angle BCD because in the given it states CD bisects angle ACD. So just write that. Now there's a couple of issues here. I could use the other given. Then again, I should start by saying this. This is a unique proof just to showcase the difference of what angle bisector and angle bisector and a midpoint do. I could use the reflexive side here. In fact, if I use this reflexive side right here, that would give me angle side. And not using the entire given, there's nothing wrong with that. I could not have used the midpoint and the reflexive side. And I'll show you guys that in a second. Okay. So, D is the midpoint of AB. D is the middle of this line here. So what that means is that this and this part, just as I mentioned in the definition section, are now congruent. So I can make that statement that line AD is congruent to line DB. And once again, I am just going to use the language directly from the given. So I directly copied the language of the given to my reason, supporting why AD is congruent to DB. Alright, let's look at a potential issue. If I would have used the angles on the side here and not used the bisector, I would end up with a situation like this on both sides. And math is a nice link. Okay. So if I didn't use the angle bisector and I just used the midpoint and the given angles, or vice versa, I would be in a peculiar situation, because I would have had to have used a reflexive side and I would have made a bad word. Geometry is a nice discipline. It's very pleasant and formal, and it never uses bad words, backwards or forwards. So we cannot prove triangles congruent using bad words. What I'm going to do now is finish this proof. So I just want to take an inventory of what I do have. I did this on the diagram. Angle, side is what I have. Angle, side. Remember, if it was angle, side, angle, the side would have to be in between the angles, which it's not. Then I'm going to check the inventory on my table. So I have angle, and a side here. So I know I've covered everything. Remember that the elements in the table do not have to be in order. But I have evidence here to prove that these triangles are congruent by angle, side. Alright, let's do the next example. As I like to, in my subsequent examples after the first one, I like to move along a little bit quicker for the sake of your time. So in this case, we have two sets of lines with the same midpoint. E is the midpoint of CD. So if E is the middle of this line, that means that these two parts here, CE, line CE, is congruent to line ED. And again, I'm just going to use the language from the given. So I should take a second and explain a minor detail that's not something that I really stick to or is important to me, but depending on who's teaching you these proofs, they could be a stickler for these types of formalities. When listing the points, technically speaking, you should be listing them in the order they are listed in the triangle, because those are the corresponding points. So I would not say that CE is congruent to ED. I could say CE is congruent to DE, or EC is congruent to ED, but I cannot swap the order. That's a formality in proofs. Just wanted to share quickly with you. Alright, so now let's take a look at the other midpoint. E is the midpoint of AB. So therefore, we also have AE and EB being congruent. So I'm going to fill this in. AE is congruent to BE as mentioned in the triangle. Then I'm going to use the language in the given. Be careful. You cannot swap these. These cannot be swapped. They are line specific. If you swap them, technically speaking, you did the proof wrong, even though you knew what you were doing. Part of the challenges with proofs, which is a challenge with math in general, is that you need to be as precise as possible in your actions and in your language. So now what I have here is I have two sets of sides. And what I notice is I have a pair of vertical angles. The vertical angles in the center here are completing my proof. So I have angle CEA is congruent to angle DEB. I actually had to look to see how the triangle was listed to make sure I maintain that order. And those are vertical angles. So one thing I want to mention about proofs that also makes them difficult is that you need to know your definitions. We covered vertical angles in a previous video on proofs. So you have proven these if you have done those proofs. And you could use that definition now to prove these proofs. It's a major life skill, as I mentioned before in those videos, and I will mention again, the application of knowledge is huge here. But that also brings with it the major challenge. Alright, let's finish this proof. So when I take an inventory, side, this is an angle and that's a side, this is a side and that's an angle and that's a side, I see that my triangles are congruent by side, angle, side. Now I'm just going to take that same inventory on my table, this is a side, this is a side, and that's an angle. Again, geometry likes nice words, but the order of this proof listed in the table does not matter. I have enough information here now to prove my triangles are congruent. So I'm going to fill that in. Angle, side. Okay. So that is that example. Alright, let's take a look at the next one. Okay, for this example, I got the first part of the given written down. And what I want to show you here is that you don't have to write the givens down all at once. It's really up to you. The only order that matters is that the fact you're using to prove something needs to be listed before it. So watch what I mean here. Angle DAB is being cut in half by AC. So this line here is cutting in half this angle. So that means I have two congruent angles here. Well, I can state that I have those two congruent angles now. And just like before, I am going to use the language from the given. This might make it a little bit easier to avoid swapping similar given statements. Now I'm going to handle the second part of the given. So I'm now addressing the second part of the given. And what's happening here is this line AC is cutting apart this angle down here, DCB or BCD. Either way, that's the same angle, creating these congruent angles here. So I now have angle DCA is congruent to angle BCA, and I'm just once again going to use the language from the given. So now I have to find a side because I have two angles. Well, I could use that reflexive side like the way we covered in the previous video. And I should take a second and make clear, you cannot pick these up piecemeal. In other words, this series of videos that I am doing really will require you to watch the first video, then this video, if you're lost. If you just need to see how to use bisectors and you have the other properties down, then great. But if you don't, go back and watch those videos, even from the previous playlist where we prove angles and lines. Okay, so now I'm going to take a inventory of what I have. And I have angle side angle here. And angle side angle here. I'm going to double check and make sure I listed those parts. I have an angle here, and a side. So I've listed everything I need to prove my triangle's congruent by angle, side, angle postulate. Alright, let's do the last example. So once again, I decided to, do not have to, break my proof into two parts by separating the given. You don't have to do that. But I just want to give you two examples if you want to play with this idea. So O is the midpoint of MQ. So that means I have MO and OQ are congruent because O is the midpoint. So I'm going to write that out. I should point out I did take the effort to make sure I matched my corresponding parts, just in case if you don't have me as an instructor, as a stickler for that. Now, I think what I want to do is address the parallel lines. So I should point out, in my effort to break up these proofs into two parts, I keep forgetting to write the second given and have to go back and rewrite this second part of the proof. So let's take a look at what we got going on. So this line here, MN, is parallel to PQ. Very commonly represented by arrows pointed in whichever direction, as long as they're the same direction, showing that those lines will never meet and forever go in that direction. In a previous video, we talked about covering or proving alternate interior angles. Just like in the previous proof that involved vertical angles, I can use those definitions. So knowing that, angle M and angle Q are congruent. And so are angle P and angle N. Here's where proofs get very tricky, because you need to have complete control of your definitions, as I mentioned earlier. But also, you have a lot of choices you can make. So in this case, I could have used the vertical angles in the middle too. And instead of using, let's say, these angles, I could have went this route. It really is up to me, as long as I'm not spelling any bad words. For this example, I chose to use both pairs of alternate interior angles. It tends to be the common choice with students. The language here for the reasoning should state that these are alternate interior angles in both cases. So I did this on purpose. I could have wrote both these angles on one line, or I could have separated them. Another issue that students often have is that they struggle to understand that you could use the same reason to prove two different facts. Another thing here, which is a little bit unique when you have specific type of angles. While I may let it go, depending on what mood I am in, typically you do not write the language of the given for these. It's considered too general. You should really state the specific angles you're seeing. Alright, let's finish this up and take an inventory of what I got going on. So in this proof, I have an angle here, and then a side outside. Then on this side, I have an angle and a side outside. I'm now going to take an inventory of my table. So I have the side listed here, the angle, and the angle. This is a critical step, because when we typically look at proofs, we do not look at the diagram. We look at the table to make sure all the facts are listed. I see it often with students where they mark off their diagrams properly and then misalign. So be careful with that. Alright guys, this was a pretty challenging view of proofs. I hope you guys found this video helpful.